Hello, this is Mrs. Lim, your physics teacher. So in this second part of radioactivity videos, we'll be covering about background radiations as well as half-life and calculations related to half-life. Okay, so basically radiation doesn't happen only with radioactive nucleus. Radiation is actually all around you. So there is something called a background radiation. So the definition of background radiation is as follows. It is the amount of nuclear radiation in an environment where there is no other radioactive source being deliberately introduced. Okay? So where does all this background radiation comes from? And it's all around you. It comes from two main sources. One are natural sources and one is artificial sources, but majority of it comes from the natural sources. So I'll go into natural sources first. Certain things that are found common in nature do emit a small amount of radiation. So for example, in your air or in the ground, there is actually something called radon gas. Okay, in certain food and drinks, especially things that is high in potassium or high in salt. Okay, your table salt, your banana. Okay, certain food also do emit radiation as well as certain amount of rocks also do emit radiations. Uh, Another natural source are cosmic rays from the outer space as well. Okay, this also creates background radiations, but you don't really need to know exactly what are those sources that causes radiation. Okay, but there is also another type that is artificial sources. Those comes from man-made. Okay, like you use medicinal X-ray. In the hospital, when it's near the X-ray room, the background radiation will be much higher. Okay, and then also waste products from nuclear power plants. Okay, which we will talk about it in the later part, in the other few parts of the radioactive videos. So, background radiation accounts for the natural one, comes from natural source, is about 80%. Okay, most of the background radiation we encounter are usually very safe and very small amount. It's about 20 counts to 30 counts maximum per minute. So it's actually a very small amount of radioactivity that we are being exposed to every day. Okay, so then after that, we move on into why do we need to learn about background radiation? Okay, because we are moving into the next part about half-life of a radioactive substance. So before we go into half-life of radioactive substance, I'm going to introduce to you how do we measure the amount of radiation being emitted by a radioactive nucleus or by any sources around you. Okay, it is measured using something called a GM counter. Okay, in short, like GM counter or Geiger-Müller tube. Okay, so usually the GM counter consists of a detector. Okay, that detects the alpha, beta, gamma radiations, and then it sends the signal over to a counter. Okay, the counter will tells you, oh, how much radiation is being detected. So a detector and a counter. Okay, so the SI unit for the amount of radioactivity, or you measure it using Becquerel, okay, BQ. Okay, but we seldom use Becquerel. Becquerel means one disintegration or one decay per second. One Becquerel is one decay per second. But we rarely use this word Becquerel. Instead, we use commonly we use counts per minute or counts per seconds. So if there is radioactive substance present or alpha particles, beta particles, gamma rays are being emitted, we measure how many counts are there per minute or per seconds. Okay, so how do we measure the amount of radiation that is being emitted? Okay, so usually we measure the background radiation. So we try to remove anything that is radioactive in the environment. That means we don't introduce a radioactive nucleus like uranium, radon, all those kind of things. We don't introduce them. Okay, just like in a home environment around you. Okay, so we place the GM counter and the stopwatch on the table. So we remove all radioactive sources, start the counter, start the stopwatch, and then time for 10 minutes, record the number of counts shown on the GM counter. Okay, so the number of counts in 10 minutes divided by 10, that will be the number of counts per minute. So repeat and calculate the average. That will give you the background radiations. Usually the background radiation is about 20 counts per minute in a natural environment. Okay, so this is as follows. Skip. Okay, then after that, if you put something that is radioactive near a GM counter, naturally the count rate will be much higher because it's emitting more radiations, emitting either alpha, beta, or gamma. Okay, and then there is something, although we say that the nuclear decay is a spontaneous and random process. Okay, we do not really know exactly when will when a particular nucleus will decay. But there is scientists has discovered that there is actually a fixed rate of decay. That means over a period of time, they can actually the amount of particles that decay, the amount of nucleus that decay, undergoing decay over a long period of time is quite fixed for different radioactive nucleus. So prediction about the decay of a large number of nuclei, okay, can be made because it has a fixed half-life. So what exactly is half-life? The definition of half-life is the time taken for half the number of nuclei of that nuclide in any sample to decay. So originally, let's say I have 400 radioactive nucleus. Okay, when after maybe 20 minutes, I drop to 200 nuclei. So it's exactly half. Initially, I have 400. Now I drop down to 200. That means 200 of them have already decayed. I do not know exactly when does it decay. I do not know which direction does it decay. But over a fixed period of time, 20 minutes, half of it would have decayed. 200 have decayed. And then from this 200, another 20 minutes later, I reach 100 nuclei. That means again, half of that 200 has decayed again, which is 100. 100 has decayed, and then I left with another 100. So it's approximately fixed at 20 minutes for this particular radioactive nucleus to decay. So that is called the half-life of that particular radioactive nuclei. So we zoom into more examples over here. So there is iodine 131. So iodine 131 is an unstable nucleus. So it is going to emit radiation in order to make itself stable. So initially, okay, I have 120 nuclei or nucleus over here. Okay, and then after 8 minutes, after 8 days, this is the number of atoms or number of the radioactive nucleus, and then this is the time in terms of day. After 8 days, so I measure every day, day 1, day 2, day 3, day 4, day 5, day 6, all the way until day 8. Okay, I realized that I only left with 60 atoms or 60 nucleus left to decay. So half of it has decayed. 120 divided 2 is half, 60. So I have decreased by 60. Okay, I left with 60, half of it only. Okay, in 8 days. Then they realized that after another 8 days, again, half of 60, which is 30, would have decayed again. So I will only be left with 30 atoms of iodine 131 now. And then after another 8 days, again, half of 30, which will be 15, will have decayed, and I'm left with another 15. So this is what I meant by half-life, okay? And this is what we call a decay curve. Okay, it's an exponential decay curve. It's in an exponential shape, means that I start from a particular number, I go down, but it will never reach zero. Okay, it will never reach zero, and it's at a decreasing rate. At the start, it's more nuclei decreasing, more nuclei decay, and then after that, I get lesser and lesser nuclei decay. Okay, for every half-life, but it's approximately a fixed amount of days that, or fixed timing that causes half of the nuclei to decay. That fixed amount of timing is called the half-life of the uh, atom. Okay, I give you more examples over here so you can take a look at this, but not every time it will be like this. So 920 drop to 60, 60 drop to 30. This is in fact considering that there is no background radiation at all. So 120 all belongs to iodine 131 atoms. But in real life, okay, when we measure about things, this is the decay curve that includes background radiation. That means I put my gem counter in a place where I have the radioactive source. It not only measures radiation from the source, it also measures radiations from the background radiation. So it is important to subtract away the background radiation first, because the background radiation uh, means that, let's say I have, so for example, you take a look at this example, you can see that the graph goes horizontal along this part. Okay, the count rate remains at about 20 counts per minute. Okay, so this is 20 counts per minute after some time. It doesn't decrease anymore. So this 20 counts per minute is actually the background radiation. It's already present there because of the radon in the air, or because of certain food substances, and etc., or because of cosmic rays from the outer space. Is naturally already there. This 20 counts per minute. So originally I have 420. Okay, at 0 times 0. I have 400, my GM counter measures 420 counts per minute. But does 420 counts all come from the radioactive source? No. In fact, only 400. I need to take 420 minus away the 20. The 20 is because of background radiation already present there. It's not because of the radioactive source. So originally, I would only have 400 counts per minute. 400 counts per minute only. Okay, then if I want to measure the half-life of this substance, so initially my count rate is 400. After half a life, I should have decreased by half. I should have reached 200. But my count rate shouldn't measure 200 because 200, I must still plus back my background radiation, which is 200, which is 20. So I should read the graph at 220. Okay, because that would mean that half have decayed and then plus another 20 from the background, 220. So I read, oh, it's approximately 20 minutes. Okay, then I can continue to see. Okay, so the count rate because of the radioactive material is only 200. Again, half of 200 will be 100. But my count rate wouldn't read 100. It will read 100 plus 20 because of background. So I go down 120. I go over here. You will see that the next half-life will be at 40 minutes. So another 20 minutes have passed, and I again, my count rate dropped by half to 100 plus 20. 120 will be at 40 minutes. And then after that, it will be 100 counts per minute already. I will drop to again another 50, half of it. But 50, I still need to plus 2, 70. Okay, 70. So it will be somewhere here. So you will see it's become 60 minutes, 20 minutes, 40 minutes, 60 minutes. It's another 20 minutes. Okay, so in terms of if they give you the count rate per minute, you need to take a look at, you need to determine how much is the background radiation first. Then after that, you determine how much is the radiation cost or the count rate cost from the radioactive source, and not because of background radiation, to do your calculations for half-life. Okay, I have also input in other videos from other YouTubers to show you about there is many sample questions on how to do on half-life questions. related to half-life. Please take a look at those examples to give you more ideas about how do we apply the concepts of half-life calculations. Okay, so the count rate of a radioactive substance decreases until everything has decayed. So over a period of time, you will see that, oh, the count rate has become stagnant at 20. That means all have already decayed. Okay, my 20 counts per minute is only my background radiation. So it will continue to drop and drop and drop until everything has decayed. Okay, so usually the background radiation is about 18 or 20 or maximum 30. Okay, it shouldn't go very high per minute. And just take note that the half-life of the isotope just now you have seen is actually 20 minutes, which we have gone through. Okay, so this is the next part. I will stop at here.